Okay, so we are looking at angular impulse, and we're going to be looking at the angular impulse angular momentum theorem. So we will write those off to the side here. So angular momentum, all right, that is given by L, and that is going to be equal to the moment of inertia times the angular velocity of the object. Okay, so we have to figure out or know what the inertia is of the object, which we could figure that out, or it might be given. And then we're going to have to figure out what the rotational velocity would be in radians per second. Okay, so that would be our angular velocity. So let's look at the scenario above here. So we have an ice skater spinning at 2.5 rotations per second, and we are given an angular, or excuse me, we're given a moment of inertia of 0.5 kilograms times meter squared. What is the angular momentum? And then at the conclusion of the spin, the skater slowly and dramatically stops, or slows to a stop over 3 seconds by dragging the toe on one ice skate. What's the value and sign of angular impulse on the skater? What average torque did the ice exert on the skater? So that ice, or the friction from the ice, is what's slowing the skater down. So we have a lot of things here that we're looking for. So let's see if we can find this first, and then we're going to write out our angular impulse and angular momentum theorem here in a second. Okay? So originally the skater is going, so that's the initial angular velocity. That's 2.5 rotations, or also revolutions is like what I like to say, per second. So 2.5 revolutions per 1 second. If we remember how to convert that from previous lessons, then we can do some tracks. So 2.5 revolutions in 1 second. And we have to think about radians here because we want to convert that to radians per second. Every revolution we're going through one entire rotation of a circle, and a circle is 2 pi radians. So we have one revolution is equal to 2 pi radians, right? So that angular, or that dimensional analysis there, our revolutions would cancel and we'd be left with radians per second. Now I don't want this in terms of pi. It might be best to drag that through the entire time, but I'm going to round this to get us a decimal to carry through. So my initial angular velocity is going to be 15.71 radians per second. So that's our initial angular velocity that we are having, or that our skater has. Okay, so we need to use this to calculate our angular momentum at that time. Okay, well, angular momentum is given by moment of inertia, which in our problem, or our scenario, is 0.5 kilograms times meters squared. And then we're going to take that times our angular velocity, which is 15.71 radians per second. Okay, so our angular velocity is going to be 7.85 kilograms times meters squared per second. So that would be the answer to our first question. Our angular momentum that we have at the beginning of the scenario is 7.85 kilograms times meters squared per second. So next, we put our toe on the ground, or the skater puts their toe on the ground and slows to a stop. So we're looking for that impulse. Okay, so remember, impulse is torque times change in time equals my moment of inertia times change in angular velocity here. And then our other equation that we could have is that angular impulse, angular momentum is equal to change in our angular momentum. So this one might be the easier one to use here, just because we don't really have to figure out a final angular velocity or anything like that. We're just looking for our impulse here. So impulse is going to be change in angular momentum here, and we found our initial momentum to be 7.85 kilograms times meter squared per second. What's the final angular momentum here? Well, the skater is going to come to a stop in 3 seconds, so we know that that's just going to be moment of inertia times final angular velocity, which is just going to be a 0 kilogram times meter squared per second. So we don't have to do a whole lot of work there just because we know it's going to be 0. So if we're trying to find angular impulse, which is torque delta time, or torque change in time, that's going to be 0 minus 7.85 kilograms times meter squared per second. So it's just going to be that negative 7.85 kilogram times meter squared per second. And the way we write the label for angular impulse is not this. We have to change it, okay, because we know that torque is in Newton meters and then time is in seconds. So that Newton meters per second, or Newton meters times second, so that Newton meters times seconds is the label for angular impulse. Okay, so that would be our next question, or our second question. So the final question that we're going to be looking at here is, what is the average torque that is exerted on the skater by the ice? So what's the torque that's causing the skater to stop? We are given a time value of 3 seconds. So now we can just take that time value and plug it into our impulse here, and then we can find that torque. Okay, so let's do that. So if we divide both sides by 3 seconds, then we get 2.62, and that will be a negative. So torque is going to be a negative 2.62 Newton meters, if we remember from torque before. So there's a negative 2.62 Newton meters exerted on the skater, which is causing that skater to come to a stop. Okay, so we related angular momentum with the angular impulse, which is time and torque, and we used the time that we were given to find the torque exerted on the skater to come to a stop. So for the last example here, we're looking at a DVD player rotating. So the DVD rotates at 25.5 rotations per second when we're looking at the inner edge, okay, and it is rotating at 10.5 rotations per second when we're looking at the outer edge. So what is the change in angular momentum as the disc is read from the inner edge to the outer edge? So let's label the inner edge as our initial momentum, angular momentum, and let's label the outside edge our final momentum. Okay, so remember, our angular momentum is the moment of inertia times the angular velocity. Okay, well, with each of these we have an angular velocity that's given, so we can write that off to the side if we want to. We have an initial angular velocity and a final angular velocity. And if we remember in the last problem, if we want to go from rotations or revolutions per second, we just multiply it by 2 pi, and that's going to get us to radians per second. So we're going to write those down below, but I'm going to have these values taken times 2 pi. So our initial angular velocity is 160.22, and that's radians per second. And our final angular velocity is 65.97 radians per second. Okay, so what we're looking for here is just our change in momentum. Okay, so that would be change in angular momentum. And if we remember from our last scenario, or from our equations, that could also be written as moment of inertia times change in angular velocity. So this is pretty easy to get, and we have our moment of inertia up above here. Okay, so let's just kind of plug that in. So change in angular momentum is going to be equal to 2.7 times 10 to the negative fifth, and we're working in scientific notation here. That's a fairly small number. If you put that in your calculator as exactly as it is there, then you should be okay. And then it's going to be final minus initial, because that is what delta omega is. So 65.97 minus 160.22. Okay, so simplify this a little bit. We're going to put this in our calculator, and we'll save the units for the end here. So putting this in your calculator, you get negative 94.25. And then we'll finish this out. And we get negative 0.0025 kilograms times meters squared per second for our change in angular momentum. If we wanted to do scientific notation just to kind of follow suit there, we'd move our decimal place 1, 2, 3, so it'd be between the 2 and the 5. So negative 2.5 times 10 to the negative third kilograms times meters squared per second. Okay, so we can see that angular momentum changes here from the inner edge to the outer edge. All right, now you might wonder why that is. Well, think about our moment of inertia here. What's going to be different if we go from inner to outer? Right, so if we go from inner to outer, you're going to have more mass towards the outside edge, which is going to change the number. So we're going to have a greater value minus a lesser value from the inside to the outside of the DVD. So these were a couple examples on angular momentum and angular impulse. So hopefully these help you out in your lesson. And thank you for watching.